Here's a problem where really most of the work is in the setup. So let's go ahead and sketch it out. Okay, first off, we have two uncharged metal spheres, and they're placed 15 centimeters apart. Now we're told that this combination of spheres has a capacitance of 24 picofarads. Okay, so 24 times 10 to the minus 12th farads. Anytime I have two separated conductors, there's a capacitance to it. Remember, our basic definition of capacitance was this. Q is equal to C times delta VC. This is the potential difference between the two conductors. This is the charge stored on one of the conductors. This is the capacitance. So really, we can think of this as the definition of capacitance. The capacitance is equal to the charge divided by delta VC. And if I have a big capacitance, that means I store a lot of charge. So if I took this conductor right here, this sphere, and I moved some charge from this sphere to that one, suppose I did that. Suppose I moved 12 nanocoulombs of charge from this sphere to this sphere. Well, then this one ends up with a charge of positive 12 nanocoulombs. But because I took these 12 nanocoulombs from this conductor, that tells me that this sphere ends up with a charge of negative 12 nanocoulombs. Speaking about this system as a capacitor, it just says this. The charge on the capacitor is the charge on the positive plate. It's 12 nanocoulombs, 12 times 10 to the minus 9th coulombs. That's the charge on this capacitor. The capacitor is the network of the two conductors. Well, since I've moved charge from here to here, there's a potential difference between the two. And since there's a potential difference between the two, basically this thing works as a capacitor. It works as a capacitor. And so we can think of this thing as having a certain capacitance. And by moving charge from here to here, we've basically charged up the capacitor. So how much work is necessary to make this happen? Well, the amount of work that's done is just equal to the energy stored in the capacitor. And we have a relationship for the energy stored in a capacitor, and it's just this, 1/2 times Q squared divided by C. So we have a relationship for it. The work that's done is just the energy stored in the capacitor. It's 1/2 Q squared over C. So our solution is quite straightforward. All we do is say this, the work that's necessary is equal to the energy stored in the capacitor. It's equal to 1/2 times Q squared over C. What is the charge on the capacitor? That's 12 times 10 to the negative 9th coulombs. What's the capacitance? We're told the capacitance as well. We're told that it's 24 times 10 to the negative 12th farads. And so we end up with a work, which is equal to a potential energy of just 3.0 times 10 to the negative 6th joules, or 3.0 microjoules. Now notice this. This is a very, very small energy. Let's see if that's what we expect. What I've done is I've transferred a tiny amount of charge from one sphere to another sphere. There is some distance between them. This is a kind of a amount of charge comparable to what you get when you rub things. When you rub two things together, you get this kind of separation of charge. You have, by separating charge, developed a voltage. You have created some capacitance, but when you do this, there's not a lot of work that's required. And so we expect the amount of energy stored in this system to be quite small. That's in fact what we find. And so our answer matches the way that we know the world works.